All right. So thanks very much, Max, for the invitation, and it's great to be able to participate in this wonderful, wonderful conference. Hope to not lower the average quality too much. So today I'm talking about statistical inference with screening and selection. So yes. So sort of this is intended as a tutorial lecture. And the sort of background or motivation for what I'm talking about today is sort of thinking about what are the guarantees that we usually get from sort of frequentist statistical procedures. So frequentist statistical procedures, by definition, are ones that are intended to control performance under repeated sampling, right? That is, if we could draw the data multiple times in a given situation, right, these procedures guarantee that certain properties would hold on average across data realizations. However, the sort of material I'm going to talk about today is motivated by the observation that the way in which statistical procedures are commonly applied, sort of in reality in the wild, frequently don't match this repeated sampling thought experiment. In particular, the main two issues I want to talk about today are, number one, that we might only write up or publish certain types of findings, or number two, we might choose the target for inference. That is, we might choose the quantity we're trying to do inference on based on the data realization that we got. And in both of these cases, standard statistical procedures can yield non-standard behavior. Oh, come on. So to sort of fix ideas, let's imagine we conduct a randomized trial of a job training program. Right? The usual thing to do after conducting such a randomized trial would be to compare average outcomes between the treatment and control groups, and then conclude that, say, the treatment has an effect if the difference in average outcomes between the treatment group and the control group is sufficiently large relative to the standard error. Right, of course, we're not limited to just comparing the treatment group mean and control group mean. We could also, for instance, analyze the effect of treatment within observable subgroups of the sample. Right? Maybe I slice the data based on location or based on prior employment history and do treatment control comparisons within those cells. Again, right, the usual statistical guarantee in this context is going to be that under regularity conditions, if treatment in fact has no effect, I'm going to mistakenly conclude that there is an effect of treatment at most alpha of the time, say 5% for the usual significance levels. Now, if we think about sort of what this frequentist or this usual guarantee is doing, right? I'm fixing a procedure, right? So I'm saying I'm going to run the experiment and take the treatment control difference, and I'm asking how it's going to perform over repeated draws of the data. However, empirical practice often differs from that idealized description, right? For example, our experimental results might only be written up or published if they're positive and statistically significant. Right, this is going to lead to screening or publication bias, right, where only a subset of data realizations get reflected in the published results. Alternatively, we might focus our analysis on the subgroup with the largest effect, right? That's going to lead to selection bias. This very helpful screen. That's going to lead to selection bias. Now, there's a large and active literature in statistics and related fields which aims to correct for both of these biases. And my goal today in this tutorial is just going to be to provide a brief review of that literature, a few of the tools that it suggests, and a few of the questions that it raises. So to sort of launch into that, I'm going to start by just talking about, and just to make sure we're all on the same page, I'm going to talk about standard decision theory without screening or selection concerns, right? So just sort of set up the decision theoretic problem before introducing screening or selection. So for the decision theory setup, actually, before I jump into that, any questions at this stage? Cool. So to jump into the decision theory setup, right? Let's suppose that we observe X, which is distributed according to some distribution F indexed by an unknown parameter mu, right? In principle, we could sort of work in that abstract setup. Today, I'm going to specialize that and assume that X is normally distributed, right, as a vector with a mean mu that's in j-dimensional space and a known variance covariance matrix sigma, right? So basically, I'm observing a draw from a normal distribution with an unknown mean and a known variance. Now, obviously, assuming that the data are normal is restrictive, but in many, many contexts, this actually will be essentially without loss of generality, right? Essentially, in many contexts, we're using a vector of estimates for some quantities of interest, where those estimates may be based on non-normal observations, but the central limit theorem tells us that if samples are reasonably large, the estimates themselves are going to be approximately normally distributed. So that's where normality is going to come from. Now, let's suppose we're interested in a parameter theta, where I'm going to assume that parameter theta is just some linear combination of the mu's, right? So absorb a normal random vector. I'm interested in some linear combination of its coefficients. For a set of possible actions A and a loss function L, I'm then going to want to choose a decision rule, which is just a mapping from data realizations to actions, in order to minimize the expected loss, right? So under the unknown parameter mu, I'm interested in the expectation of the loss function evaluated at the action dictated by my decision rule and the realized x, along with the true parameter value theta. And then, of course, we might also require this decision rule to satisfy some additional constraints. Again, just to make this more concrete, let's go back to the job training example. In the context of the job training example, right, the vector X could collect treatment control differences across J demographic subgroups, right? So again, maybe I'm cutting by location, maybe I'm cutting by previous employment history, whatever. I do the treatment control differences across those subgroups, that gives me X. Now, as long as the number of trial participants in each subgroup is large, right, the central limit theorem is going to tell me that the treatment control contrast is going to be approximately normally distributed, centered around the sort of expected treatment control contrast mu with some variance covariance matrix sigma, where if these groups don't overlap, that covariance matrix is going to be a diagonal matrix, right? So non-zero entries on the diagonal, zeros everywhere else. Now, in this context, right, we could think about what target parameters theta we might be interested in. If I let omega j be the population share of group j, and I let v be the vector that collects the vector population shares, one parameter I might be interested in is just v prime mu, right? If I write out what that is, that's just the weighted average of the mu j's weighting by the population shares. Since mu j is going to correspond to the average treatment effect in subgroup j, this weighted average is just the population average treatment effect, right? What is the average effect of this job training program over the population of trial participants? Alternatively, I could take V to be the J standard basis vector. That is the vector with zeros in every position except J where it has a 1. In that case, V prime mu is just mu J, right? The average treatment effect in subgroup J. Now, what about the loss function? So if my goal is estimation, right, if I want to estimate the effect of treatment, I could take the action space to just be the real line and think about squared error loss, right? In that case, this expected loss function object I wrote down before becomes just the mean squared error, right? So this is just the expected squared difference between my estimate and the true effect when the true parameter value is mu. Right? In addition to thinking about mean squared error, maybe I want to restrict my estimator. Right, so Jan yesterday was talking about unbiasedness. In this context, unbiasedness would just say that the expectation of my estimator is supposed to equal to theta for all mu. Alternatively, maybe I think about median unbiasedness. So I require the median of my estimator, or the overestimation probability of my estimator to equal 1/2 for all mu. Alternatively, we could not think about point estimation and instead think about confidence intervals. So for confidence intervals, I would take the set of actions A to be the set of closed intervals in the real line. I could define the loss to say be the length of my interval, right? So basically I want short intervals, but require that my interval cover the true effect with probability at least 1 minus alpha, right? So the probability that theta, the effect of interest, lies in my confidence interval delta of x must be at least 1 minus alpha, no matter the underlying configuration of parameter values, right? And maybe I want to impose some other constraints as well. Now, it turns out that the problems I just wrote down have well-known solutions. Specifically, the maximum likelihood estimator for theta, which literally just looks at the same combination of my experimental results as I was thinking about in the underlying parameter space, that's going to be the best median unbiased estimator for theta, in the sense that for any other unbiased or median unbiased estimator theta tilde, right, the expected square difference between this estimate and the truth is less than or equal to the expected square difference of any other estimate in the truth, right? So this achieves the smallest possible mean squared error over the class of unbiased or median unbiased estimators. Similarly, right? If I just calculate what the standard error of this estimator is going to be, the 95% confidence interval, the confidence interval that just takes my usual estimator, adds and subtracts a constant times that standard error, is optimal in various senses, right? For instance, if I take the constant equal to 1.96, that's the usual t-test confidence interval. Now, so that's sort of standard decision theory stuff. So apologies for the review for everyone for whom it was familiar. In writing down that decision theoretic setup, though, I made two assumptions, namely that we care about performance on average across all realizations of X, and that the target parameter theta is the same for all realizations of X. And both of those assumptions can fail in practice. I'm going to refer to failures of 1 as screening and failures of 2 as selection, right? So basically we're doing screening if we only care about some realizations of X. We're doing selection if what parameter we care about depends on the X that got realized. Sort of, this is useful shorthand for today. I do want to warn you, these are not terms that are consistently adopted in the literature. So sometimes when people talk about screening, they mean 1. Sometimes when people talk about selection, they mean what I call screening, etc.
It also doesn't really map onto the econ theory version of these names, right?
Fair enough.
I'm asking you.
Well, it depends a little bit what you, I mean, in how would you map it in the econ theory sense?
Or your screening models with adverse selection models.
Yeah, but right, so adverse selection models will actually look, no, that's fair. Like adverse selection models, the people you end up with will look a little like screening. Yeah, I mean, if you have a better suggestion for terminology here, I needed some terminology to use for this lecture. So you prefer some other terminology or have suggested? That's great. Yeah, perfect. But yeah, no, I would say I had zero attachment to this terminology. I just needed some shorthand for this. So, inadequate shorthand title, screening. So, in what I set up so far, I was averaging performance across all realizations of X. Right? However, in many cases, we might only care about performance over a subset of data realizations. To formalize this, suppose that for a screening variable S, we have two properties. First, the conditional distribution of S does not depend on mu, given X, right? So basically, once I know X, to know the distribution of S, I don't need to know mu. And second, we only care about behavior conditional on S equals 1, right? For instance, I only care about the expected loss conditional on S equals 1. I only care about the expectation of my estimator conditional on S equals 1. Or I only care about the coverage probability conditional on S equals 1. Again, to sort of make this more concrete, let's go back to the randomized trial example. So in that example, suppose that theta corresponds to the average treatment effect over the population. Right, I've already said randomization is going to ensure that theta hat, right, just the in-sample estimate of the average treatment effect, is going to be unbiased for theta across data realizations. Right, but we have a fair amount of evidence at this point that not all estimates of theta hat are equally likely to be published. Right, there's an extensive literature that expresses concerns about and provides evidence of publication bias. Right, just to give a few recent examples, Open Science Collaboration 2015, Bruns and Ioannidis 2016, and Kammerer et al. 2016 basically are thinking about and providing empirical evidence of publication bias in a variety of different settings. Now, to sort of map publication bias into this screening framework that I set up, let's let S equals 1 be an indicator for the event that a given estimate theta hat gets published. Right, so just S equals 1, indicator for the event that estimate theta hat is published. Now, I've assumed that the conditional distribution of S given X doesn't depend on theta, right? Which means that publication decisions depend only on estimates and not on the underlying parameters once I hold the experimental results fixed. Right, so the assumption I'm making here is that basically the decision of whether to publish or not just depends on what you obtained in the experiment. There's not some other channel through which the sort of true parameter value affects the decision to publish conditional on the experimental results. That is an assumption, it can fail, but there are a lot of reasonable models you can write down for publication decisions where that would be true. Or at least models you could write down. We could argue about reasonableness. Now, even in this setting, publication decisions could depend on many other factors. right? For instance, there could be a preference for positive results. There could be a preference for surprising results, or alternatively, there could be a preference for results consistent with the previous literature, right? You can tell stories where any of those is possible, just depending on how you think the publication process goes. For today, I'm going to focus on an example drawn from a 2019 paper of mine with Max, where there's a preference for statistically significant results. And one reason for focusing on this case of a preference for significant results is there's a lot of this literature on publication bias where this is sort of what people point to and are worried about. Yes?
I should I be thinking, the flow to publish results on things, and what you're doing, what you're wanting to do is understand how to do this sort of meta study.
Yeah, well, you could think about it as a meta study, or you could just say, right, in papers where there is in published experimental papers where there is in fact no effect, right? So people sort of tried some treatment, and if I tried it in an infinite sample, I would get that it did nothing. I could ask what fraction of published confidence intervals in that subset of papers cover 0, right? And so so one reason you might want to know that is exactly to aggregate across studies in sort of a meta study way. But you could also think about this just in the context of a given study, right? So just in this individual study, should I trust the confidence interval or not? Does that make sense? Other questions at this stage? Great. So to sort of write things in a bit of a simplified form here, let's let Z here denote the Z statistic, right? So that's just my estimate divided by the standard error, right? Which is just my estimate normalized to have variance 1, right? And just denote the normalized effect, so that is the true effect divided by the standard error by omega. And let's suppose that results that are significantly different from 0 at the 5% level, right? That is where the absolute value of Z is bigger than 1.96. are 10 times more likely to be published than our insignificant results, right? So put in sort of the formalism of this model, that just says that the probability that S equals 1 conditional on S is 10 times larger when Z is larger than 1.96 than it is otherwise. Right, and the question I'm going to be interested in is what effect does this sort of screening have on the distribution of published results? So here I'm showing you 2 aspects of that. On the left panel, I'm showing you the median bias of published estimates as a function of the standardized effect size W. Right, so this says that among published studies where the true effect is 0, the median estimate is in fact 0. By contrast, as I increase the effect size, right, for instance, the median effect size of a published study where the median estimated effect among published studies where the true effect is 1, right, is in fact about 2.4, right? So basically, we're systematically overestimating the effect sizes in published studies where the true effect is small. As I increase the effect size further, that effect dies down, and we're basically back to unbiasedness by the time the standardized effect size is about 5. Right? Why is this happening? Right? Well, essentially, right in this context, right, the publication process has a preference for estimates, for basically standardized estimates that are sufficiently large. Right? But then if I think about a study where the true effect is, say, 1, right, that means I'm substantially more likely to get published when I overestimate the effect versus when I underestimate the effect. And as a result, when I think about the stuff that makes it through the publication screen, right, it tends to inflate effect sizes in exactly this way. Similarly, I can think about the coverage of nominal 95% confidence intervals. So that is, how often does my point estimate plus minus 1.96 standard error confidence interval cover the true effect in the population of published studies? Right here, I'm plotting that coverage in blue, while the nominal 95% coverage that we sort of think this should have under the usual repeated sampling thought experiment is plotted in gray. Right, we see that for true effect sizes of 0, published confidence intervals cover the truth only about 65% of the time. As I increase the effect size, that comes up, actually goes above 95% for a little interval here, and then comes back down. So by the time the standardized effect size is 5, I'm right back at about 95%. Yep.
Sorry, what happens if it goes above 95%? Like, what does that mean?
Oh yeah, so this just means, right, so sort of imagine the true effect size is 3. Right, so if the true effect size is 3, right? Basically, there are two ways, and the study gets, so first, under this publication model, right, we could say effectively when the true effect size is 3, you're always published, or sort of, you're always published up to a coin flip. So then there are basically two ways that I could fail to cover the truth, right? Oh, sorry, when the estimate is above 1.96, you're always published or always published up to a coin flip. When the true effect is 3, there are two ways I could fail to cover the truth. I could overestimate, right, get something basically 5 or bigger, or underestimate, get something 1 or smaller, right? But basically with this publication selection, if I get something 1 or smaller, I'm also less likely to get published, right? Because basically the preference is for significant results. And so basically for effect sizes in this range, actually the screening on statistical significance kills some of the observations where my confidence interval would fail to cover, which is why I end up covering more than 95% of the time. Now, eventually it comes down. So once the effect size is big enough, this goes away. But this is sort of a general feature where sort of you undercover some places, you overcover some places. Yeah, absolutely. Other questions?
I have a suggestion for the name of this.
Yes.
Screening.
Screening? Perfect. I personally, I really like that suggestion. But I'm also open to others. So,
Sorry, I meant to say selection.
Selection. Okay. Okay. If you like selection, sure, we could call this selection. Then I need a name for the other one. But yes, absolutely. We could call this selection. That's great. Now, while I've discussed this issue in terms of publication bias, note that it doesn't actually matter who is screening the results. For instance, one story here is that journals are choosing not to publish stuff, right? So sort of if I get an insignificant result, the journal won't publish it. But for the issues I'm talking about today, you actually get exactly the same issue. It's just the authors choosing not to write out the results. Right, so just I get a statistically insignificant result and sort of stick it in the file drawer, the so-called file drawer problem. Right, so in that sense, screening, as I'm discussing it here, also covers many forms of so-called p-hacking, right, where basically you're worried about researchers doing a specification search, researchers choosing to report results in some cases and not others, right? Many of those are going to fall into this category. Moreover, I should also note that some practices that are recommended on other grounds also generate the same issue. For instance, right, if I fit a model, but then I decide whether or not to keep the results based on the specification test, basically, does my model appear to fit the data? That actually generates these same issues, right? S equals 1 only if I pass the specification test and keep the model. Yep.
Is there a relevant case of like a marginally insignificant result dynamically incentivizes researchers to do more experiments?
Yeah, so that's a great question. So that is a case that actually does not quite fit into this framework, right? Because basically the framework I have here is basically you get your results X, you get S, and then either you see X or you don't see X, right? That would be a setting where sort of a researcher draws an initial X, and then a researcher makes a decision about what else to do, right? So basically the researcher could stop and publish that X, or the researcher could sort of pull the lever again, get an X star, right? Where X star, the conditional distribution of X star given X is something, right? And basically then the researcher would have a dynamic stopping problem. And what you would observe would be whatever the researcher had at the point at which they stopped. That also totally generates issues of the same problem, of the same type, right? There's a statistics literature showing that sort of stopping of that type can generate big biases, big distortions in standard confidence intervals, but it sort of doesn't quite fit into the formalism that I've written down here. Other questions? Great. Now, fortunately, there are some results in statistics that provide powerful tools to correct for screening. So let f of x given theta denote the density of x without screening, right? So this is just the original density of x. For what I've been talking about today, this would just be the normal density. Sorry, that should be a mu, not a theta. Sorry about that, mu. Bayes' rule is going to imply that the conditional density of x given s equals 1, right, is basically this object. So I'm going to take the original density, That is not helpful.
Martin Weidner figured out a trick how to do avoid this. Nobody.
Sadly, that trick is lost to history. There we go. And now we get to do this. Okay. So, right, basically what I'm going to do is I'm going to take the original density. I'm going to upweight values of X that are more likely to end up in the published sample. And then I'm going to rescale so the whole thing still integrates to 1, right? And that's going to give me the conditional density of X given S equals 1. Now, the reason this formula is helpful is number one, it tells us that if we knew the publication rule, right, we basically knew the conditional mean of S given X, we could calculate basically how this screening is distorting the published distribution. But it also has some other implications. Specifically, for those of you familiar with this, it is basically going to say that if the original distribution has exponential family structure, like the normal distribution, then the screened distribution also has exponential family structure. Right, and results in statistics are then going to deliver optimal median unbiased estimators and optimal confidence intervals for the target parameter theta. Right, so basically, once we know this, we actually know how to do optimal inference. In particular, in the paper with Max, we worked out what that is in this simple example where you're 10 times more likely to publish significant results than insignificant ones. And that's what I'm plotting here, right? So the thick blue, so the gray lines here are the usual estimator and the usual 95% confidence interval, right? Where I'm varying the standardized estimate on the horizontal axis. The thick blue line is a median unbiased estimator that corrects for these screening issues, right? And what you see is basically that you deflate effect sizes until you hit the usual significance threshold, at which point you start converging back to the usual estimator. Similarly, the thin blue lines are the upper and lower bounds for a 95% confidence interval, right? You see that the corrected interval is actually tighter than the usual one when effect sizes are small, shifted downwards from the usual one as effect sizes get a bit larger. And then once you pass the significance threshold, it starts converging back to the usual 95% interval. Yep.
So if I see a t statistic of 2 in the paper, I should read 1.7, 0.7.
Yeah, right. Basically, if you see a t statistic of 2, your sort of estimated effect size should be about 0.7. Yeah, that's exactly what it's saying for sort of median unbiased estimators under this publication rule.
Right, yes.
Right, I should note this is sort of under the assumption significant stuff is 10 times more likely to be published. So that piece you have to know. But yeah, exactly. So this sort of gives you a formula where if you know the publication rule, here's how you correct for the effect of publication to get median unbiased estimates or correct confidence intervals. That make sense?
Yeah.
Awesome. Other questions?
Is this kind of like Hackman type selection correction or?
I mean, the logic is in some sense very related, right? You're basically looking at something that survives a screening or selection event, right? Yeah, maybe rather than screening, I should call it truncation, right? Because actually, sort of mathematically what it is you're basically truncating the distribution and only getting the parts where S is equal to 1. So in that sense, it sort of is similar. The sort of underlying math justifying this particular correction is different, but right, sort of the intuition of sort of you're looking for things that have survived a screening event of some sort, that's the same.
To ask about the specification test.
Yeah.
They seem so virtuous to check the specification test before you even consider publishing.
Yep.
How can this be misleading to your future readers? I'm kind of lost.
Yeah. So the issue is I almost completely agree. So basically, I do think, right, that in some sense, if I'm using a model and then I sort of, the model has certain testable assumptions, I check the testable assumptions and they're rejected in the data, that does seem to pretty strongly suggest that I should sort of then not publish that result because it's based on a rejected model. The only problem that comes up is your usual standard errors are calculated under an assumption that you're not doing that, right? Because basically, if you are doing that, right, what your standard error should do is quantify the variability of your estimate conditional on surviving a specification test. right? But if the result of the specification test is correlated with your estimate, right, then basically once I condition on surviving the specification test, the distribution of my estimator changes. Right, and so that's what introduces this screening problem. Right, and so I mean, and just to preview where I'm going, right, as I'll say at the end of the talk, it's not clear to me, like I think there's a pretty good argument that screening is not always a bad thing. Right, so basically, as this specification test example points out, maybe we are screening and we should be screening. And the issue is then just what should we then do about inference? Right, so maybe the message here is not stop screening. Maybe the issue is make sure the inference we're using is consistent with what we're doing with the data. I should also note there are sort of some special cases, sort of cases like efficient GMM, for example, where actually you do get independence and things work out, but lots and lots of cases they don't.
It's not just about the standard errors, right? It's also about the bias of the point estimation.
Sorry, yes, yeah, sorry. Yeah, I said standard error, but it's the whole distribution of your estimator, the whole distribution of your test statistics. Yes, that's right. Thank you.
Can you just use resampling to sort of control all these things? And we can just do it. I did my procedure a million times on some bootstrap samples, if I did sets and go on distributions that way, doing my specification tests.
Yeah, unfortunately, Bootstrap does not in general fix these issues. So they're sort of again, I'm jumping ahead a little bit as I will talk about at the end of the talk. Sample splitting actually does fix these issues in general, but you pay a price in terms of power, right? So I could run my specification test on half the data, decide what to do. If I survive, run the estimate on the other half of the data. That will fix it, right? But then I'm running my estimator on half as much data, and like maybe I don't want to multiply the standard errors by √2 in every application I'm thinking about, right? Unfortunately, Bootstrap turns out not to fix these issues, or it's a little bit delicate. If I say that what I want to do is, in the case where my model is exactly right, I want to ensure that sort of running my specification test will not sort of mess up my estimates, then I sort of Bootstrap per se won't do it, but sort of I can simulate stuff. There's relatively simple things I can do that are going to patch this up. The problem then comes what if the model's a little bit wrong, right? So it's a little bit wrong in a way that your specification test only detects half the time. But then conditional on surviving the specification test, your confidence interval doesn't cover this sort of the target parameter that's actually being estimated by your method in that case with the correct probability. Right. So basically, the problem, basically what I would say is there are simple simulation-based corrections that people are not doing but could do that would patch things up exactly in the case where the model is exactly right. In the case where I want to allow sort of ensure robustness when the model is a little bit wrong, I think you actually could, I mean, for sure you could adapt these sort of ideas based on this, but it's not something that people are it's not something I'm aware that people have actually done. But basically like adapting this formula to that case would solve that issue. But again, does not correspond to what people are doing in practice at the moment. I have a former student. Just to give one example, if you think about one example of specification testing of this sort is like difference in difference type models where people check parallel trends, right? So basically I've got a treatment group, I've got a control group, I want to check that they're moving in parallel before the implementation of some policy, and then I'll interpret whatever happens afterwards as sort of the effect of the treatment. Right, something people very often do is plot those parallel trends in advance of the treatment being implemented. And if you see that basically the treatment group is on this trend and the control group is on that trend, you say, doesn't look like the parallel trend assumption holds, let's not publish it. So I have a former student, Jonathan Roth, who's now at Brown, who basically showed that under a fairly broad class of assumptions, screening on parallel trends in that way actually amplifies the bias of your difference in difference estimator conditional on surviving the screen. So basically, just the mechanics of how that screening works means that basically, if my estimator was a little bit biased, right, the parallel trend assumption failed a little bit before I did the screen, in the event that sort of I do the screen, but I fail to reject, the bias gets bigger among the published things. And he sort of uses this type of approach to correct for that. just one example of where I know people have worked out the specification testing connection. Other questions? Cool. So that was screening. Next, selection. So for screening, we only cared about some values of X, but we always cared about the same target theta. For what I'm calling selection problems, and again, very open to better terminology here, we want to conduct inference on theta of X, right? Which is basically V prime of X times mu, right? So basically I'm changing which combination of the mu's I want to do inference on, depending on the data X realization that I got.
Sure, it's a better name, but mixing in some way captures some of it.
Okay, that one I don't like, I'm sorry. But yeah, no, I get, yeah, I mean, I'm mixing across different target parameters. Yeah, okay, no.
And mixing estimated distributions in a way.
Yeah, that is true, but I'm actually, so let's come back to mixing, because one question that's going to be here is, do I want to mix estimating distributions or not? So we'll talk about that actually at that point exactly in a second. So selection problems of this type have been extensively studied in the recent statistics literature, where basically it's largely been motivated by model selection concerns, right? The idea is, suppose that I'm sort of using the data to tell me which model to use, and let M of X be the model that I select when the realized data are X. I can then define theta of X as the target parameter under that model, right? So for example, Burke et al. 2013 talked about this as post-selection inference. Fithian et al. 2017 talked about this problem as selective inference. So this is sort of, they talk about this as selection, but I'm very open to wanting to use different terminology here.
So if you go back to your statistical decision theory, you've got X in the loss function. That's
Yes, exactly. Right. You have X in the loss function, or another way to put it here is you have a random target parameter, right? Of basically the target parameter moves depending on what data realization I get. That's exactly right. Right. I should note that selection problems of this type also arise outside the context of model selection, though. So again, let's go back to this randomized trial example. There, right? Remember, X records treatment control differences over these J different subgroups. Now, in that context, we might be interested in the effective treatment for the group for whom the treatment appears the most effective, right? So let me define J hat as the group where the treatment control difference is largest, and then define theta of X as the element of mu corresponding to J hat, right? So basically, I look over these many different subgroups and I say, oh, treatment was really effective here. That's where I want to do inference, right? That's what that approach is. You might say that seems like a weird thing to do, but I'll point you to an empirical example in a minute where actually this is very, very close to what happened. Alternatively, we might be interested in the average effect of treatment across those subgroups for whom it appeared effective, right? So I could define basically V of J as basically looking at whether was treatment effective for subgroup J. If it was, weight it proportional to its population share. If it wasn't, weight it to 0. Right, or alternatively, if you don't like thresholding at 0, I could say the average over groups where there was a positive and statistically significant effect, right? That would just replace the 0 here with some standard error-based threshold. Now, as with screening, right, selection of this type generally invalidates conventional inference approaches. To illustrate that, I'm going to use an example from a paper of mine with Adam McCloskey and Toru Kitagawa. In particular, one thing we do in that paper is to calibrate a simulation to data for a randomized trial of job training programs that was conducted across 13 different sites. Specifically, the data here is coming from the Job Start experiment, which was conducted by the US Department of Labor. Now, as it turned out, in this experiment, the program at one of these sites, specifically in San Jose, appeared the most effective. And that site was subsequently selected as the model for a replication study. Right, basically, so they took the model at that site, rolled it out at a bunch of new sites, and then found that basically when they rolled it out, the results in the replication were disappointing, right, relative to the results of the initial experiment. And so a question you could reasonably ask, right, this example has very much the structure I just gestured at, right? I ran an experiment across 13 sites, I took the site that looked best, and then I rolled that model out at a bunch of other sites, right? And the question is, how much bias should we have expected that procedure to induce? So to think about that, we're going to take the experimental results from that trial as the starting point. We're basically going to sort of pretend the true effects of this intervention at the 13 sites are proportional to the estimated effects in the trial. We're then going to scale those effects up or down to vary the degree of treatment effect heterogeneity across sites. For a given effect size, we'll then simulate draws of the experimental results, right, and ask how selecting the site with the largest estimated effect impacts inference. Right, in particular, our preferred scaling basically scales the effects to match an unbiased estimate for the true variability in treatment effects across sites. Right, so here I'm showing you the median bias of the usual estimator. Right, so again, I'm simulating data from these 13 sites, picking the winner, comparing the estimated effect at that site to the true effect. And we basically see that we're, at our preferred scaling, we're substantially overestimating the effect of treatment. Basically, this is a pretty low income population. We're overestimating the effect of this job training program on earnings by more than $2,000. Right, that's actually a pretty substantial upward bias. The estimated effect at the best site in the original trial was around $6,000. We can also think about the effect of coverage. Right, so how often does the reported 95% confidence interval for this preferred site cover the truth? We see that at our preferred scaling, it's covering the truth only about 80% of the time, right? So we're substantially undercovering the true effect at our selected site. Right, and so this example illustrates that, like screening, selection can invalidate conventional inference procedures, right? The estimated effect sizes are biased upwards, conventional confidence intervals undercover. Now, this selection, as we were talking about, this selection problem introduces a new wrinkle relative to the analysis so far, namely that the target parameter theta x is now random, right? Basically, for different data realizations, I've got different target parameters. Coming back to the conversation with Max, this suggests two possible routes forward, right? One thing we could do is condition on v of x, basically condition on the target parameter I've chosen, and so remove this randomness, right? To take your mixing terminology, this is sort of conditioning out the mixing. Or we could not.
It's like inference on the maximum versus inference on the J that was selected as the maximizer.
Exactly, right? It's sort of inference on the maximizer rather than inference on the maximum, right? I think there are various arguments why inference on the maximizer corresponds to a site we actually know, right? Whereas inference on the maximum says, I don't know which site is the best, but how good is the unknown best site?
How does either approach relate to an empirical base approach, say, where?
So basically, so in the sort of small scale version here, so basically, the thing in this case, right, the thing that is in fact messing up inference is that my target parameter depends on the data, right? And basically, I'm sort of conditioning on the data before choosing my target parameter. Now, Bayes is fully valid conditional on the data, right? So if I took, say, a full-fledged subjective Bayes approach, I believe my prior, this issue goes away. For empirical Bayes, right, if I'm sort of trying to estimate my prior from the data, if I have 13 sites, it's hard to do a great job estimating my prior, right? If I have lots
of like change time at 3 sites, you can estimate the prior.
Yeah, no, but the issue is, so that's where I was going. I'm not talking about it today. We have another application in the paper where you've got sort of lots and lots of parallel units, basically census tracts in large metro areas. And there, the problem is that empirical Bayes will completely resolve the issue if you consistently estimate the prior, right? But basically, in practice, what people often do is say put a normal prior on stuff in the style of James Stein. You can show that generates severe undercoverage.
But if you do non-parametric empirical Bayes,
then it gets delicate, right? Because then essentially the issue is, right, what am I trying to do inference on? Right, because the problem, for example, if you think about the full winners problem, I'm trying to do inference on the very best. That my posterior distribution on the thing that's on top is going to be very sensitive to the tails of the estimated prior, but tails are sort of by construction hard to estimate well, unless I have some kind of parametric structure. Now there are other cases, right? In the example we use in the paper, you want to do an inference on basically the average quality over the top third of tracts. Right there, right, you're putting a lot more weight sort of towards the middle of the distribution. my guess would be that sensible empirical based procedures ought to work like it should be there a way to get empirical based to work there. But no one, I'm not aware
That's
of
my
anyone
question is like
having worked that out.
one step before like these details of like estimated performance, just like conceptually how these two questions of inference on the maximum, inference on the maximizer relate to like an empirical base type. Like, I mean, they're all trying to correct in some ways for an upward bias, right? But slightly different ways. Like I said, I have wrapped my head around how they.
Yeah, so empirical, right? So basically, empirical Bayes is totally happy with this version, right? Because you would basically just look at what do I think is the best thing? What is my posterior distribution on that thing, right?
Yeah.
And so then sort of, if as long as I'm happy with my prior, the Bayesian version of this totally works and is very, very simple. Inference on
the coverage rate of that, say, for a confidence set based on that, then the coverage rate would be valid conditional on what?
Conditional on the distribution of true effects being drawn from the prior.
Right, but not conditional on the theta itself. Or
No, not conditional on the theta.
Yeah.
Yeah, not conditional on theta. But if I believe the prior, I mean, it's valid conditional. It is valid sort of under the prior, even if I condition on the winner, even if I condition on any other function of the data, that's fine. But it's not, but it's valid in the base sense. It is not valid in the frequency sense. Yes.
Right.
That's
So it's really like predicate sets versus confidence.
Yes, exactly. But I mean, what I would say is here, if I have a good model for the distribution of effects, I would be totally satisfied with validity in the base sense, right? The issue is just you sort of need, in many of these cases, getting a good model on the distribution of effects when you have 13 sites. I'm not so confident.
So maybe there's another remedy here, though, is after the fact, which is that we should never have done as many as tried as many as 13 different things in the first place.
I don't know. I think I'm a little. I guess I would, in some sense, right? If we think we have a job training program that's potentially effective, but we have these various models for doing it, right? I guess my inclination would be instead to say, I mean, if we have the sort of ability to do it at that scale and the expected, I guess it depends on what's the expected social payoff of adding an additional site, but I could easily imagine cases where it's sort of worth having 13 sites. And my view would instead be, we just need to be cautious about we need to be aware of what we did in focusing on the winner and adjust our conclusions accordingly.
But it could be that if we had been more sparing and done, say, 4 different things, then we actually would have had a better chance. Take no total procedure without to recommend.
It's actually a really nice paper that Pepper and co-authors one.
On tail.
So basically, depending on the true distribution of effects, right? It depends. Like if you have a fat tail, then you might want to run many small experiments. If there is more effects concentrated in the vicinity of 0, you want to run a few large ones.
Okay,
no,
right.
Yeah, and actually just so to preview where I'm going here, actually, it turns out that basically so we develop some methods to correct these issues. We do go back and apply them to this example. And it actually turns out that applying them to this example, the disappointing performance is not entirely explained by the winner's curse. So sort of even accounting for sort of this upward bias due to picking the winner, you actually still have a statistically significant effect at that sort of bit at that site that performed best in the experiment. And what looks like actually happened is that basically there's sort of various institutional stuff, like the center that performed the experiment in San Jose was basically really plugged in with local employers, sort of was not actually comparable to the other 12 centers, and was also not comparable to the center where things got rolled out later. And this actually relates a little bit to the flavor of things in Lily's talk, right? Basically, the job training program treatment here was really very different depending which of these 13 sites you talked about, but in a way that wasn't realized until they tried to take the one and scale it up, and they couldn't. But yeah, I mean, so basically, I think it depends on what the setting is, depends on what you think the distribution of effects is, all that kind of stuff.
I'm sorry, this is a random open-ended question. I'm sure it makes sense, but could you write the surprising effect bias in one of these setups? Because that seems like a statement about the distribution of alternative beliefs or something like that.
Yeah, so what I mean, so one version of the surprising effect bias you could easily write in the screening setup, right? Of basically I let S equals 1 if the effect is surprising. Right, and basically the distribution of my estimator is going to be biased conditional on the effect being surprising. Right, because unbiasedness basically averages over the surprising and boring data realizations. So you can definitely write that in the screening setup. I mean, in this setup, you could also do a version of that where in some sense, if I'm running many different results and then I focus on the most surprising one. Right, that sort of would fall into the selection setup where basically J hat would select what's the most surprising result. Does that make sense?
Yeah, I think so.
Yep, okay, excellent. Right, it's just a distinction of sort of, do I have one result? Anyway, do I have one result and I'm basically thumbs up, thumbs down, is it surprising or not? Versus do I have a list of results and I'm picking the one that's most surprising? Is the screening versus selection distinction. Excellent.
First time somebody's done that.
It's so rad. There we go. You know, people need hobbies. That's great.
It is being published.
Oh yeah, there we go. Exactly. Oh, my grace is being preserved forever. That's wonderful. So as I was saying, in this case where the target parameter is random, right, we basically have an option of sort of, do we condition on the target parameter selected or not? So by conditioning on V of X, right, what I mean here is requiring conditional median unbiasedness or conditional coverage, right? So I could require that the median of my estimator is equal to the true parameter value conditional on being interested in that particular combination of effects, right? Similarly, I could require that I cover the true parameter value conditional on, oh, sorry, this should be 9. This should be 1 minus alpha. Sorry about that, not a half. Conditional on targeting that specific combination of effects. Right, however, right, once I do this conditioning, I'm actually immediately back to the selection case, to the screening case, right? Screening, not selection. Once I do this conditioning, I'm immediately back to the screening case, right? Basically just defining S as an indicator for the event that I target that particular parameter, right? So basically I take selection, but then condition on the target parameter, right? That basically just turns it back into screening, and we immediately know how to construct optimal estimators and confidence sets, right? That's what I was just talking about for the screening case. Right, and this route was advocated by Fithian et al. 2017, right? A quote from their paper: our guiding principle is the answer must be valid given that the question was asked, right? So basically this is saying, I want my inference statements to be valid conditional on the event that I decided to ask that particular question about that particular target parameter. But we don't have to do that, right? I could also think about unconditional inference or unconditional coverage. Right, so I could just require that the median of the difference between my estimate and the true parameter. Oh man, another typo. Sorry, this is Vx prime of mu, right? X of theta, right? The median bias of my point estimate is 0, or that the coverage probability is 1 minus alpha without conditioning, right, on the target parameter. And why would I do this? Well, one reason is that unconditional inference is less demanding. Right, basically, if you give me something that's conditionally valid for all possible target parameters, it's also unconditionally valid just by the law of iterative expectations. But that means that the class of unconditionally valid procedures is bigger, right? So if all I care about is unconditional validity, maybe I can get shorter confidence intervals, maybe I can get more precise estimators. Now, Berg et al. 2013 sort of had an initial proposal for unconditional inference, which amounts to forming a joint confidence set for mu, right? That is data-dependent set mu that covers this vector of all the effects with probability 1 minus alpha, and then forming a confidence interval for x by basically asking what values of theta x are consistent with that joint confidence set for mu, right? Essentially, I'm forming a joint confidence set for this whole vector, and then taking that projection of that joint confidence set on the particular linear combination I happen to select for this data realization. Now, doing that turns out to ensure unconditional coverage, right? Basically, this coverage statement gives me the coverage statement for the random target parameter theta of x. But it also ends up giving us confidence sets that are much longer than necessary much of the time. On the other hand, An advantage of this approach is that we actually don't need to know V, right? We don't need to know the function, which tells us the mapping from data realizations to target parameters to implement this approach. Instead, all I have to know is what target parameter did I want for this data realization. Now, in the case where B is known, right, basically where this mapping from data realizations to target parameters is something that I know, my co-authors and I propose a hybrid approach that sort of combines conditioning and projection. Again, going back to this job start randomized trial example, here I'm just showing you the median length of the usual confidence intervals. At the bottom here, I've got the conventional confidence interval, right? So that's nice and short, right? This is median length in tens of thousands of dollars, right? That's nice and short, but we know that it undercovers, right? We know that it's too short. In the circles here, I've got the projection interval, right? That's longer, right? And sort of, not by a lot, but it sort of stays long even in this case, where there's sort of one site that's much, much, much better than the others. And we actually saw there wasn't much bias in the simulations over here. The conditional interval is the triangles here. We see that it starts super duper long, right? More than 3 times as long as the conventional interval when the treatment is not very effective. But it's like eventually converges down to the usual interval. Finally, the squares here are the hybrid interval my co-authors and I suggest, and you sort of see that it does pretty well on length throughout here. That's what we're selling in that paper. Here, my point is just that once you know that you're in the selection problem, there are ways to correct for it. So before I move on to open questions, are there questions here?
So one justification for having the model size thing is that you kind of vary the treatment at each of the different sites.
Yeah, exactly.
Right. So you might think that so is this about deconvoluting that actually being heterogeneous effects and that it's just randomness?
I mean, it's a little tough to tell those apart, right? In the sense that like the flavor of job training program that was implemented in San Jose was different from the flavor of job training program that was implemented in Buffalo, but also the labor market conditions in San Jose were different from the labor market conditions in Buffalo, right? So sort of this study was not designed to tease apart sort of what's coming from the sort of program design versus what's coming from the labor market conditions. You could think about designing a trial to do that, but this one sort of, you had variation across sites in both of those dimensions, right? I mean, they were hoping it was about the program, which is why they scaled it up.
This also would this apply to like large RCTs with like a lot of arms, for example, like they want to say.
Yeah, exactly, right? Of sort of I try 50 different treatments and I'm picking the one that looks best. This whole framework applies directly to that. Yeah.
You know how badly like the projection or hybrid approach do in terms of conditional coverage, especially with small scaling.
Yeah, I mean, basically you can make the conditional coverage arbitrarily bad. Basically, you can drive the conditional coverage to 0 for either.
By scaling the effects to 0.
By basically scaling effects negative. Like basically, so think about, imagine I've got, right, even just imagine I've got 2 treatments and one is great and one is terrible, 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 terrible. Now, some of the time, right, if the sort of, in large samples, the terrible, 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 terrible one will still win some of the time, right? It's a vanishingly small part of the time, but some of the time. And conditional on that event, the projection interval is going to fail to cover, right? Because basically, like I'm conditioning on the event that I sort of got the order flipped, which tells me that I almost certainly got a huge realization of the estimation errors.
Yeah.
And so that's actually part of what drives the length of the conditional so high, is that you're trying to protect yourself against that event, right? You're trying to protect yourself against the event that one of these is super bad and I just got really unlucky and I have to condition on that.
But the scaling to 0 is actually where all the effects become 0, right? So it's not that
but so here, so the thing is here I'm showing you what happens for the arm that is best in the original study. But imagine I extended the scaling negative here. Right, so basically, as I extend the scaling negative here, the arm that was best in the original study becomes the worst arm, right? And so then I would be looking at sort of how often am I covering? Oh, actually, sorry. Here I'm integrating over everything. But you could extend the scaling negative and basically think about what happens conditional on the worst arm winning. And if you think about what happens conditional on the worst arm winning, the conditional still has coverage 95%. Everything else has coverage converging to 0 as I make the worst arm.
But
worse
it's
and
also
worse.
an event that has vanished probability.
Exactly. Yes.
Okay.
So you've just said you're interested in unconditional coverage. Or almost, right? Basically, so exactly. So that event has vanishing probability. And so if I say it has vanishing probability, I don't care about it, that's very close to saying that this is what I care about. Or sorry, this is what I care about.
Yes, sir.
Right. Does that make sense? So with that, let me turn to a few open questions. So one thing that I've gestured at a little bit, but I think it's helpful to draw out here, is that the sort of available techniques to correct for screening and selection impose very, very high information requirements. Right? For screening, I need to know this conditional probability, right? To sort of deploy the corrections I was just suggesting, right? So I need to know what's the probability I'm interested in this thing conditional on the results. But, you know, thinking about how we often do empirical work in practice, I think this is actually not such an easy object to think about, right? Because it's not so easy to say, oh, for this data realization, I would, you know, for sure be interested. I would for sure write this up. For this one, I have a 49% chance of writing it up. For this one, I have a 6% chance of writing it up, right? Fully specifying that over the space of all possible data realizations is quite hard, right? Maybe I get a data realization and things look funny in a way that I forgot to sort of write down in advance, which sort of says I don't know how to write this thing down. For selection, we either need to know, again, this function V, right? So basically, if I got this data realization, I would be interested in this target parameter. Or we need to know the set of possible target parameters theta x, right? So for theta x, I don't need to know sort of exactly when I choose each target parameter, but I need an exhaustive list of all the target parameters I might sometimes be interested in. In many contexts, all of these are kind of demanding. Right? Basically, we don't necessarily have an explicit description of like what is guiding every choice that we make when we're doing empirical research. Now, in some contexts, we may be able to estimate screening or selection goals based on observed choices, right? If we sort of see the choices that people are making, we can say, oh, hey, it looks like this is what people are doing. Let's correct for that, right? And that's the idea of my paper with Max on publication bias. In other contexts, right, we can clean these issues up by sample splitting, right? I could basically say, I'm going to screen or select based on part of my data and use the remainder of the data for inference or estimation, right? That does clean up all these issues, but comes at the cost of reducing how much data we're using for inference.
Which in a way is what replication studies are about too.
Yes, exactly, right. I mean, exactly. You could think about replication studies as sort of a targeted way, right? Where basically I do the original study that screens, then I do the replication study just on the treatment that I picked out or just on the things that survive. That's exactly right. I mean, it turns out the same arguments that say sample splitting is inefficient also say that if I truly believe effects are constant, I actually want to pool results over the initial and replication studies, but that's sort of a second order point.
Yeah, could you enter more into detail into how you aim to try to estimate the probability of publication conditional on the actual?
Yeah. So great news. We have a paper about it if you're interested. But yeah, I mean, essentially the idea there is if I sort of have access to sufficiently rich data or am willing to make sufficiently strong assumptions, I can basically back this object out in the publication case. Right. So for instance, one context we do is basically replication studies. Right. So imagine that sort of I've got like a perfect replica. Imagine that sort of for every published study in some body of literature, someone performs sort of a perfect replication study. Right. So sort of the ideal version would be, you go to the same group of subjects, you randomize the same treatment, blah, blah, blah. If that were true and there were no publication bias, the distribution of original and replication studies is going to be symmetric. Basically, that joint distribution is going to be unchanged if I flip which I call the original and which I call the replication, right? Because I'm just performing the same experiment, the noise realizations are going to have the same distribution. I can just flip them. Now, if you do that plot, though, things are highly asymmetric. And basically what we show is you can use that asymmetry to back out this non-parametrically in that context. Similarly, there's basically many of the other meta-study methods people use make an assumption that the effect sizes in a given study are independent of the standard errors. So basically, it's not the case that studies that are more precise have larger target parameters or vice versa. That's a super duper duper strong assumption, but like nonetheless, it is implicit in like many of the things that people are doing in the meta-study literature to sort of try to correct for publication bias. We again show that if you're willing to believe that assumption, it non-parametrically identifies this object.
Anytime you've got big data, sample splitting is much. So is that not problem solved? At least for that category of problem big data.
Yeah, well, I mean, again, there's different ways for data to be big, right? So as long as you have sufficient data that you're not worried about sort of substantially reducing the portion of that data that's available for inference, yes, right? Basically, you can just split sample, do the selection on part of the data, do sort of the inference stuff on the remainder of the data, problem solved.
But if I'm maybe follow up, that's like, I mean, that's kind of gets back to the topic of the workshop, right? Which it's problem solved if there's one person and they want to do the right thing. But if there's conflict of interest across different parties, then that doesn't really solve anything because it would have to be a data split where one part of the data is kind of hidden away somewhere.
Yeah, that's true.
So it gets back to the whole social nature of learning, I guess.
Yeah, that is true. Right. So yeah, in some sense, if someone else is doing the selection and I don't totally trust them, then I have to be able to sequester the half of the data used for inference away from that. Yeah, that's true.
If people start to use the pre-commit to this analysis, this way to playing with the data, would that solve an issue? Or the fact I don't know because people still don't end up working on that because like in practice, what
Oh yeah, that would solve it. Yeah, no, right. I mean, basically, right, if I say I'm going to run this experiment, and if the results come out like blah, 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 I'm going to throw them away. And otherwise I'm going to write them up. I've just specified what this is. And so I could just do inference correcting for that, and I'm done. Yeah, so in some sense, if I sort of have a fully specified contingent plan of what I'm going to do.
Which is what a pre-analysis plan is supposed to be.
Exactly, is a version, exactly. Yeah. Right. I think one issue is sometimes I run, I go to the data and like I see something I was not expecting that throws me off, but it could at least report the things I said I was going to report, do this, and then do other stuff. Right. But yeah, for sure. If I have a fully specified pre-analysis plan that includes like sometimes I throw away the data, that's okay. That sort of gives you that.
So would you say that having a system in which like the pre-analysis plan is like a paper is accepted based on a pre-analysis plan is similar to say the editor doing the splitting for the researcher?
I think it's a little bit different from splitting, but it completely resolves these. I'll talk about that in a second. Yeah, it totally resolves these issues, but yes, I would say it totally resolves these issues. That leaves there's a separate question of whether that means that's what we should do or something else. But yes, that totally resolves these like statistical issues.
Both or like that being?
Oh, sorry. So it totally resolves the screening issue. And basically it would also allow, right? If basically the pre-analysis plan said, oh, if I get data realization this, I'm targeting this. If I do data realization that, I'm targeting that. You would then need to do the selection corrections, but that's fine. You can do that.
But I was comparing that with, like, the splitting being done by somebody who's, I guess, to use the language from yesterday, an expert, but then not involved in the research, so doesn't have the kind of like.
Yeah, well, I guess I would the line I think I'm trying to draw is that pre-commitment is different from splitting.
Okay.
Right. In some sense, pre-commitment is telling me I know either this or V of X.
Yeah.
Splitting is basically using part of the data to do the selection or screening and then only using the rest for inference. So sort of pre-commitment, I get to use the whole data for inference.
Yeah.
But I have to specify these things. Sample splitting, I don't have to specify these things, but I'm losing part of the data.
But for sufficiently large data, it is the same, right?
For sufficiently large data, maybe I don't care about the data costs, is the way I would say.
Yeah.
Right. Yeah.
What should we do about like people lying about P probability as equals 1?
Yeah.
And so, just to,
Yep.
so the way I understand what you're saying is, if the report X equals the probability, and that's the true probability, you're supposed to treat it in the correct way, but if they're lying, then that's like completely bogus, so.
Yeah, exactly, right. If I told you, or what about lying about V of X? No, I was always planning on doing inference on, right, white females aged 26 to 32 living in Des Moines, whose sister is Black. No, that was always who I was going to do inference on. What are you talking about? No, right? So basically people just saying like, I'm sort of picking a subgroup in a totally ad hoc way, but sort of not admitting that's what I'm doing. Right. Well, if I don't, that I would put that in the category if I don't know what people are doing, so I can't apply these corrections. Right. So again, right, one way to solve that, coming back to what Max was saying, is right, if I can do the split sample, right, I hold back part of the data, I make them tell me what they're going to be doing inference on and what their estimator is based on the other part, and then I run it. That fixes it, but that's costly.
I mean, I think an interesting question version of what Quinton and others were asking is, what's the class of mechanism we can and should consider once we start thinking about these conflicts of interest?
Yeah.
And pre-registration or commitment is one of them. There's a question: does it in some sense contain the optimum or not?
Right. That is a great question, and yeah, sort of right.
Which kind of closely ties into this, right?
Yeah, I mean, in some sense, what I would say, right, what this does is basically, if I know these things, here's how I can correct for them statistically. And then I think then I would say there's then the related question of sort of under what set of mechanisms is it incentive compatible for people to truthfully report these things, right? And that's the way I would basically split it, is sort of, once I know these, here's what to do, but how do I elicit those things in a truthful way, I think is a super interesting mechanism design question.
But there's not the related question. It's like if there's another class of mechanisms like adversarial refereeing or sample splitting with a third party or other things, maybe under what conditions do they dominate this approach or not? And
yeah, I mean, I
guess
in some sense, yeah, this almost isn't quite that's a little tricky in the sense that you don't, like, you can do adversarial refereeing, that's going to imply one of these. You could do sample splitting, that's going to imply one of these that sort of is totally fine and doesn't generate any problems. So in some sense, I would say many of those can be cast into this, but I agree in some sense there's the question of how do you get the ingredients to apply this?
I mean, maybe this is a reduced form of everything you can do. I think that's one possible answer.
Exactly. I think that is my answer. I'm sort of a little hesitant to make that broad claim without having like fully proved it, but like
conjecture.
I'm having a hard time thinking of something that does not generate this as the reduced form.
Yeah.
But
with an interesting debate formally.
Yeah, exactly. I was going to say that is not a theorem.
We just need more journals.
More journals would be good. Yeah, I mean, right. One thing is the more acceptance rates. As an editor, I would say 100% acceptance rate would make life very easy, but people would probably get upset with me. So I think can't pre-commit to that. But yeah, exactly as this whole discussion ties on, right? I think this raises a question of sort of, are there better options, right? Sort of, are there other things we should be doing here?
So when I was working on finance, we definitely use sample splitting, even if it didn't meant starting with seemed like really useful data. And we would force the researcher to have no access to most recent data. It tended to be best to be most recent data.
Yep.
And then a researcher could develop a reputation for being prone to overfitting, over modeling, or not, or maybe a more experienced researcher would be less likely. And the best researchers would have a greater hit rate when they saw unseen data. I'm not sure how we think about that problem, how to do. I think it comes a bit back to where I was going when I was asking earlier whether it's best to only try 4 things. What a really good, what experience? Sorry, what heuristics a good researcher should use in order to have a better chance of producing genuine results.
Yeah, and I mean, I think that's a really good question. So, for example, one way to cast that is sort of you can generate basically a version of like the this sort of selection problem in like a backtesting, like a finance backtesting type example, right? And basically just imagine I've got a list of possible trading, or got a space of possible trading strategies. I estimate how good each of them are on historical data, and then I pick the one that does best, right? That induces exactly this type of bias. Sample splitting does clean that up. And what you will see there is basically that, right, depending, I mean, it somewhat comes back to what Max was saying, is in some sense there's a, depending on what my prior is on what do I think the underlying distribution of true effects is, right? I can end up with very different places in terms of what optimal sort of backtesting or optimal experimentation looks like there, right? Basically, if I think that, you know, things are sort of, there's some things that are better, there's some things that are worse, but the effect sizes are sort of fairly concentrated. What I'm going to want to do is sort of pick the ones that I think might be, pick a small number of ones I think might be good, and then take the best of those. Because if I take a lot of things, basically the penalty I'm going to pay, or the deflation I'm going to get is going to be huge. On the other hand, if I think that there's sort of, you know, most things are meh, and then there's a small set of things that are going to be amazing, right? Maybe I actually want to take a larger number of things because when I get a winner, right, it's so good that I can afford the price that I'm paying for trying many, many things. Right. So in that sense, it's sort of the trade-off really depends on what do I think the underlying distribution of effects is. That makes sense?
Yeah.
Right. So coming to something else we've been talking about a little bit here, right? We saw that screening invalidates conventional inference procedures. Right. That motivates one thing that's been motivated by that, tied very much to the discussion we were just having, are procedures that try to reduce screening, like pre-analysis plans or pre-registered reports, right? So basically pre-result peer review, right? Basically you send the plan for the study to an editor, the editor sends it out to referees, and basically the decision to whether to publish it or not is based on the protocol for the study, not on the results. However, right, to the point we were talking about, that isn't the only option, right? Sort of there are many, many other things we could do, and as long as we know the form of screening, we can correct for it. Right, so sort of if I know the form of screening, I can give you valid frequentist confidence intervals. And moreover, there are cases where it seems like there's a fairly strong argument that screening is helpful. Right, one example in a paper of Max's with Alex Frankel is that screening in favor of surprising results can be optimal for a journal looking to inform readers. Right, if I only have the ability to publish a small number of articles, right? And basically these articles contain actionable information. Well, I want to publish the results that are going to change what people do, right? And so in that sense, in that setup, it's optimal for me as an editor to publish stuff that's surprising. And then I could clean up frequentist inference on the back end if that's something I want to do. Alternatively, right, as we were talking about earlier, screening based on specification tests is a common and quite explicit suggestion. And it seems a little funny to say, oh, I've run this model, it fits the data terribly. But here's the result, right? Like maybe if it fits the data so bad, I should go and try and find a better model. And so in both of those cases, I would say it's not so clear. The answer should just be don't screen, right? Maybe the answer needs to be figure out how we're screening and just make sure that whatever we're doing is consistent with the screening we're doing. But again, this comes back to the mechanism design question. Can we truthfully elicit sort of how we are screening all of that? Finally, when the target parameter is theta x, right, the target parameter depends on the data. Some open questions include whether we should condition on the target parameter selected, right? Basically, this issue of sort of, do I need to ensure that my confidence interval is valid conditional on the question that I'm asking? Or is it fine to just average over different questions I might have asked? And then more of a technical question, but it's not so clear what the framework is for optimal inference once the target parameter is random. That's sort of not the sort of usual setup in statistical decision theory. So at least I would be interested in someone working out results for that case. So that's it. Thank you all very much.
I'm just going to ask clarification question.
Yeah.
Is it different for somebody to sort of p-hack as a case of selection, which is trying to work out, okay, there's a significant effect of subgroup, versus including a lot of treatment arms in an experiment in the hope that one of them hits? Do you see them as conceptually equivalent things? Or?
I mean, I guess there's a little bit of a So there are different ways to include many treatment arms, right? So one thing I could do is just include many treatment arms, but then correct, right? But then like standard practice would be to correct for the multiplicity, right? So if I'm trying 50 different treatments, right, I maybe say, oh, I'm going to do some correction for the fact that I'm doing, and I do 50 different things, one of them works. I'm going to do like a multiple testing correction for the fact that I tried 50 different things, right? That would generate valid coverage, right? I mean, that's actually closely related to projection, which I talked about here.
So you can do that for like the acting into honest, right? Like you can say,
Yeah. Yeah, but I would say, right, sort of honest, a version of that, I would say sort of honest p hacking is basically saying, here's what my v is, here's what my s is, and then basically accounting for that in inference, right? So sort of in that sense, right, it is in principle fine and something one can do in a pre-analysis plan to basically say, oh, if this control shows up as significant, then I'm going to include it. If this control shows up as significant, I'm going to include it. If this interaction shows up as significant, I'm going to report that. And then like you could specify that complete contingent plan of what you're going to do for every possible data realization, and then correct for it in this way or sort of in a multiple testing-y way as appropriate. So in some sense, if you're in this world where you sort of have everything pre-specified, you're transparent about what you're doing, and like you yourself can describe what you're doing, like these corrections apply and sort of in principle can fix everything. And the issue is just you'll pay a power cost.
So in practice, I think this applies quite nicely to data that is collected or experiments. But if you think of like exploratory data, like data analysis, like people are like, oh, I'm exploring this thing.
Yeah.
I think themselves don't even know
Yes.
that they're doing
Exactly. Yes.
p hacking or whatever.
Yep.
So how do you think about that in this framework, or is it at all?
Yeah, I mean, I would put that exactly in this category of I would say that's a case where like I don't have an explicit description of what's guiding my choices. Right now, in an experimental setting, right, maybe that's okay, right? Because I run a pilot, I sort of do a lot of exploratory data analysis and figure out what I think is going on. Then I write my sort of plan for the main study and I run the main study and I sort of execute the thing according to my plan, right? That again comes back a little bit to the flavor of sample splitting, where like the sort of exploratory sample is the first bit of the data, the remainder is the rest. But sort of two things I would flag there. One, right? So for example, like what do we do about macro? No, but like, right, like in some sense, macro, right? Like, you know, think of how many papers have been written on US aggregate macroeconomic data going back to, you know, World War II. Right, it is thousands upon thousands upon thousands upon thousands of papers, and saying that like, oh, we're gonna pause publishing macro papers for 50 years until we have another 200 observations to sort of sample split. That seems like it's probably not going to happen and probably shouldn't happen, right? And so that's a case where like it sort of seems totally hopeless. We don't have the fallback of sort of saying, oh, you could do your exploratory data analysis in the pilot and then run the main study, right? Or like these commonly used data sets like the PSID, right? Like how many people have used the PSID, right? So in some sense, I guess I would say, so the answer I gave of like, do the exploratory data analysis and then do something else, I think works for settings where that's an option. But I also think there are lots of settings where like, that's not really an option.
But is there a way to kind of design some measure, which is not a confidence interval, but some sort of cost of, like, you know, take it with a grain of salt, but the grain of salt that is a bit more metric based than
Yeah.
I don't know.
I mean, in principle, like again, right, like a fully Bayesian approach resolves this. But like if I'm analyzing the PSID, is my prior really not informed at all by the data in the PSID? So like it's not so clean. Like, yeah, I don't have a great answer.
It doesn't address the PSID or macro question, but in some ways, I guess the stuff that Jan was talking about, right? At least in principle, solves both issues when you say have two research teams and each gets half the data for exploration and then validation on the other data set. Then in principle, you don't need to have the fully specified function and you don't waste the data. I mean, I'm not sure how many sense is practical, but
so one thing I would flag is that the sort of CrossFit thing works as long as we have the same target parameter. Right. The problem is in the selection case, we have different target parameters on the two halves of the data. And so I can't like, wait, maybe that's fine because like I learned two cool new things today, right? Rather than like one cool new thing. But like I can't just aggregate them.
I have a bit of a ill-formed meta question, which is you started out with this base decision theory model, and it kind of suggests that the solution is to be found by shrinking towards a prior when there's not much data, or for example, by taking some decisions based on that. We could say, maybe as an editor, you should just accept experiments based on the pre-analysis plan before the data is available. But effectively, it would kind of mean you would use your prior to think about, is this likely going to be interesting?
Yeah.
So I'm wondering whether there's one risk that if we approach the world this way, we're exactly missing out the things that go against our existing beliefs. So do we actually have good enough priors to think about the world in this way?
Yeah, I mean, it's, not
Exactly,
not to talk about Max's paper in front of Max, but like,
Yeah.
I sort of think of that as, right, like in some sense, in a world where like we all share the same prior about what's going on in the world, but I have access to a subset of results and I have to choose which of them to tell you. I should tell you the surprising ones.
I do agree with it. I'm more like wondering, like, as we model all this, like, are we in a way running a risk that by just modeling it this way, we are exactly like I like the result by Max and Alex on exactly it should be the surprising thing, but like how do we model surprising if we may have the wrong priors in the first place? Or like just from a methodological point of view, would you advocate actually explicitly writing models where we have uncertainty about whether our priors are correct or something like that?
Yeah, okay. I mean, so
What it amounts to that paper is like surprising is everything that changes your action.
Yeah.
Right. So there's a default action that kind of sets the baseline.
Right, but I feel like I could put them into a Bayesian framework, and then I would still not do something where my prior is basically zero, that it's going to produce a surprise. So this is why it's an informed question.
Yeah.
Like
I mean, the paper I'm going to present on later this week is basically going to take the perspective of like, I as the sort of data analyst don't know what the right prior is, but there's some set of priors that's out there in the audience. And my goal is just going to be give the audience information that they think is going to be useful. And if they disagree about what's going to be useful, I have to choose how to aggregate. Right. So that's sort of the punt I'm going to use because I don't know how to answer that quite like.
Right, and I think it makes a lot of sense because I'm kind of a bit worried that we are pushing towards protocols that make everything super replicable, and by either pre-specification or by even accepting reports there. But where is the avenue by which we learn something totally new?
No, and I mean that's sort of right to me, like the specific, like right. I strongly agree with that, and I mean I also do think that's sort of why to me like that. The specification testing example kind of fits that, right? It basically, I thought this analysis was going to be the right way to go at this data. I see the data and I realize my analysis is dumb. Should I, like, just saying like I should run the dumb analysis seems the wrong answer.
Yeah.
Saying I should completely kill the project also seems the wrong answer. I should do something.
But I feel like the priors are also very dependent on like the weight of the prior of the editor is a lot heavier than it should be, right? In some ways, if we think that there is an audience for a paper, it shouldn't be, when an editor changes, the way the papers that are submitted are completely different, and also then so what surprising means is also interesting there because that is surprising conditional on on a given editor.
Yeah, right. I mean, in some sense, right? Like. Right. I mean, this is an issue of sort of the people screening the papers in principle should be serving the interests of the audience. But I mean, right, you could have editors who all think they're doing that, but they disagree what that is. Right. I also am conscious that we're at the end of time, so I'm very happy to continue the conversation, but also want to let people get snacks and coffee. So thank you all very much. And happy to hang out and chat more.